In this video, I will discuss the problems assigned from Chapter 10 of your textbook. In problem 10.7, you are given this circuit here, and you are asked to use nodal analysis to find V. V is going to be a phasor noted by this particular node here. V is going to be at this node at the top middle portion of the circuit. You've got a voltage source that's already been converted to a phasor. We've got two different resistors, one here and one over there, and we've got an inductor and a capacitor that have already been converted into the frequency domain, and we have a current source here in the middle that has already been converted to a phasor. And so really what we're going to do is effectively a lot of the same exact math that we already learned previously when doing nodal analysis. In this case, all of the currents into the node labeled V have to be balanced by currents going out from the node. And so in this case, we have this voltage minus this voltage divided by the total impedance between. So we have 120 phasor symbol minus 15 degrees minus V over the total impedance, which is going to be 40 plus J20, equals the current going out. So we have 60 phasor 30 current leaving here through the current source, plus V over negative J30 ohms. That's going to be the current leaving the node through the capacitor, plus V over 50 ohms. That's going to be the current leaving through the 50 ohm resistor. And so what we can do here in order to divide this phasor by this complex pair is go ahead and convert the complex pair here into a phasor. And so we're converting 40 plus J20 into a phasor. Here we're finding our R value, here we're finding the angle. And so what we get there is 44.7214 phasor symbol 26.5651 degrees. And so now we have that in here, and we are dividing those two phasors, and we're subtracting off this other phasor, and that is going to equal V over these various complex impedances. And so we can go ahead and divide these two phasors, just divide the amplitudes here and subtract the angles from each other. So there is the division there, and now we're subtracting off 6 phasor 30 degrees. So what we're going to do is go ahead and expand both of these and do that as you see here. So we have the amplitude times cosine of the angle plus J sine of the angle minus 6 times the cosine of 30 plus J sine of 30. And that is going to equal this complex pair that you see here. And that, of course, we can go ahead and say equals the right side. And what we are doing on the right side is we are getting this into a common denominator. And so here first I've begun to get a common denominator of 50 and negative J30. So there is the common denominator there. And then we can go ahead and combine that with the 40 plus J20 that we have right there. And so here we get the right hand side with proper common denominators, and then we expand that on out, go ahead and multiply these complex pairs together. Then we are going to gather our like terms, and we get this complex pair multiplied by this complex pair divided by this denominator. So we're just distributing everything on through. And so V ultimately is going to equal this total complex pair. Just done this out in MATLAB. Then we convert this to a phasor. We go ahead and we get the magnitude as the square root of this squared plus this squared, and then we get the angle as the inverse tangent of this divided by that, and ultimately V is equal to 124.086, phasor symbol, negative 153.9603 degrees. In problem 10.25, we are asked to find the current I naught in here. And we can do that using mesh analysis. In this case, we don't need to use superpositioning because our omegas are the same. We see that we have an omega equals 2. And we also see that this is in sine form. And so I'm going to go ahead and convert that into cosine form before I convert everything to frequency domain, so that way I can make a phasor in cosine form for both voltage sources. And so here we see 6 sine of 2t is equal to 6 cosine of 2t minus 90 degrees. And so we convert everything into the frequency domain. And so here we have our 10 cosine of 2t is just going to be 10, 0 for the phasor. Our 6 sine of 2t is going to be 6 minus 90 degrees. That way we have it in cosine form. And then our resistor is going to stay the same at 4 ohms. And our capacitor is going to be 1 over j omega c. And so you see here we plug in the omega of 2. Our C was 0.25 farads. So when we multiply everything out, and then we can multiply by j over j, we get a negative 2j ohms for the impedance of the capacitor. And then we get a Z of the inductor is j omega L. So that's going to be j, omega is 2, L is also 2, so we get 4j ohms. And now what we can do is mesh analysis around 2 different meshes. So we do an I1 mesh and an I2 mesh, and we know that I naught is going to equal I1 minus I2. So if we can solve for I1 and I2, then we can go ahead and subtract those two and get I naught. So going around this mesh, we're going to have minus 10 phasor 0 plus 4 ohms times I1 plus negative 2j ohms times I1 minus I2. And that, of course, is going to equal 0. And so that's what we have right here. This is our I1 mesh equation. Then if we go on to the right, we have an I2 mesh. So we have I2 minus I1 times negative 2j ohms plus 4j ohms times I2 plus 6 phasor symbol negative 90 degrees. And so we have this right here. That, of course, also equals 0 by Kirchhoff's voltage law. And now what we're going to do is get this into matrix form. So we take our 2 mesh equations, and anything that is multiplied by I1 is going to end up here. So this becomes 4 minus 2j ohms. So we have 4 minus 2j right there. And then what's multiplied by I2? In this case, you're subtracting 2j ohms, and this is also subtracted. So when you multiply those negatives together, this becomes a positive 2j. And that's going to equal 10 if we take this constant 10 and move it over to the right-hand side. So that is our top entries in the array. We're going to put these into this array form, coefficient over here, constant on the right-hand side multiplied by I1 and I2. And then in our second equation, our I1 coefficient is just going to be negative 2j times the negative 1, so positive 2j. And then our I2 coefficient, we have negative 2j plus 4j, so that's going to work out to positive 2j. And then on our right-hand side, we're going to move this phasor value over. And we can go ahead and convert that into a complex pair, knowing that for 90 degrees, the cosine is equal to 0, the sine is equal to -1, so this just really becomes -6j. We have our angle completely in the complex domain. So we have -6j right there, and when we move it over to the right-hand side, it becomes +6j. And so we can solve this just by plugging it into MATLAB and then taking the inverse of the A matrix, multiplying it by the B matrix, and so that comes out to 2 plus 0.5j for I1, 1 minus 0.5j for I2, and so I0 is just going to equal our I1 value minus our I2 value. So we have 2 plus 0.5j minus 1 minus 0.5j. That works out to be 1 plus j. And so now we can take our 1 plus j value and convert it back to a polar coordinate. So we get our r is going to equal the square root of 1 squared plus 1 squared. So we get square root of 2. Our angle here, since we have a 1, 1 for our two legs of the right triangle, is just going to be inverse tangent of 1 over 1. So that's 45 degrees. And so ultimately our final expression for I0 of t is going to equal this r value, square root of 2, cosine of, put back in our omega, 2t plus 45 degrees. Moving on to problem 10.45, we're asked to use superpositioning to find I of t. And in this case, we have two different voltage sources, and you notice that they are operating at different omegas. This one is 10, this one is 4, and so we have to use superpositioning in order to determine this current. And so what we're going to do is actually break this down into two different circuits. We're going to keep one of the sources at any given time, convert everything to the frequency domain in terms of all of our other components, while shorting out the other source. And so for the source on the left, omega is 10, the source on the right, omega is 4. And we're going to replace our inductor here with j omega L. And so here is our first circuit to be analyzed. You see that we have converted this into our phasor notation. The 20 ohms just remains the same, and j omega L in this case is j times 10 times 300 millihenries, or 300 times 10 to the negative third. So this becomes 3j ohms. And so to get this current, we just take the phasor and divide it by 20 plus 3j. That's going to be our total impedance of these two components. And so we're going to convert the 20 plus 3j into a phasor. So here you see square root of 20 squared plus 3 squared, inverse tangent of 3 over 20. And then down here, our I prime is going to be found just by dividing those two phasors. So 8 over 20.2237 gives us 0.3956, and 30 minus 8.5308 gives us 21.46. And so I prime of t, that is the current based upon the influence of just the voltage source on the left, is going to be 0.3956 cosine of 10t plus 21.46. Now, we analyze a second circuit, and here we've already converted this voltage source into a phasor. And in this case, we go ahead and convert our impedance here for the inductor into a j omega L. Omega here is 4. L is still 300 millihenries. And so this works out to j times 1200 times 10 to the negative 3, or 1.2j ohms. We do pretty much the exact same thing as what we had before. And so in this case, our I prime prime is just going to equal this voltage phasor divided by the total impedance that you see there. And in fact, this actually should have a negative in front of it. I think I missed putting that in your solution. So because the current is actually going to go in the opposite direction because of the positive and negative here. But anyway, we still go through the same basic procedure like we did before. We convert the denominator, the total impedance, to a phasor. And here we see 3 divided by the amplitude of the other phasor. We're subtracting the angles there. And so we ultimately get 0.1497 cosine of 4t minus 86.8664 degrees. And that should be actually going in the opposite direction of the current, so we should actually subtract that off. And so I is going to equal I prime plus I prime prime. And so if we add together those two currents, this should actually be a minus right here because that current is going in the opposite direction. And also your textbook answer converts this second sinusoid back in terms of sine, which you can very easily do. And it also converts it into milliamps, and so you can just move the decimal 3 places to the right. So that's 10.45. And then the final problem that was assigned for homework, you're asked to use this op-amp circuit to find VO divided by VS, which is the gain, and then also to find VO of t when VS of t is equal to Vm times sine of omega t, and also when omega is equal to 1 over RC. And so in this case, what we have with our VS here, we are going to go ahead and convert our capacitor into an impedance, and so that becomes 1 over j omega c. And now we know, because we've seen a lot of op-amps in this configuration before, this is going to look just like a regular inverting op-amps configuration. In this case, we see that the current flowing through R must flow through the capacitor C. And so we have the current through R is just going to be Vs over R. We know that because there is negative feedback, so that means the voltage at the negative or inverting terminal is the same as the voltage at the positive terminal. That is grounded right there. So Vs over R is the current through that, and that has to equal 0 minus V naught over the impedance of the capacitor. And so we see that right here. And so now if we go ahead and rearrange some of our terms, what we get is Vs over R is equal to negative V naught, and because this is divided by a 1 over j omega c, we can just multiply by j omega c right there. And then if we go ahead and rearrange this algebraically, we divide through by V naught, multiply through by R. What you get is V naught divided by Vs is equal to negative 1 over j r omega c. And in order to get this j out of the denominator, we multiply by j over j, and we get j over r omega c is the gain here. Now, if we go ahead and plug in what we were asked, if omega is equal to 1 over RC, then V naught over Vs is just going to be j over RC. And so in that case, what you're just going to have is j. And so if Vs of t is equal to Vm sine of omega t, then when you plug in this and convert it into cosine, it becomes Vm cosine of omega t minus 90 degrees. Convert this into phasor. What you get is V naught divided by this Vm value is equal to j. This is our gain right here. And so then if we wanted to find V naught, we just multiply j by the phasor that we had there. And effectively, that is going to change our real and imaginary axes. And so then this becomes just Vm, because cosine of negative 90 is equal to 0. Sine of negative 90 is equal to negative 1. And then what we have inside of here then is just negative j Vm. And then when we multiply that by j, we end up with positive Vm. And so we have that, and so V naught is going to equal Vm with a phase offset of 0 degrees. So you can write that as Vm cosine of omega t plus 0 degrees volts, or Vm sine of omega t plus 90 degrees.